Welcome. We are in 7.7. We are graphing of 4 remaining trig functions: tangent, cotangent, cosecant, and secant. Knowing what values to pick off the unit circle are very important for these 4 functions. So let's start with the tangent function. And here are the properties of tangent. The domain is all real numbers except integer multiples of pi over 2. The range is all real numbers. The tangent function is an odd function, meaning it's symmetric across the origin. Tangent is, its function is periodic with a period or cycle or revolution of pi. The x-intercepts are multiples of pi, and the vertical asymptotes occur at odd integer multiples of pi over 2. So the asymptotes and the domain should always go hand in hand. So the domain says all real numbers except integer multiples of pi over 2, and the vertical asymptotes say they occur at odd integer multiples of pi over 2. Okay, so let's graph the tangent function, and let's find out what points to pick. All right, so remember that, I have the unit circle here for a reason. So when you choose points for tangent, remember tangent puts x over y, y over x, sine over cosine. So if you are picking points for tangent, 0 looks pretty good. You put 1 over 0, you'll get, I keep saying it backwards, sorry. You put 0 over 1, you'll get 0. Perfect. You don't want these coordinates, that's just messy. Let me actually reduce the size of that. So 0 is a good pick because it puts 0 over 1, which gives us 0. Pi over 6, not a good pick. 1/2 over square root of 3 over 2. We can graph that, but we don't like graphing anything messy, so we won't use that. Pi over 4, perfect. It puts square root of 2 over 2 over itself, which gives us 1. So these check out. Pi over 3, ugly as pi over 6. Don't want that. Pi over 2, perfect. It'll put 1 over 0, which will give us undefined. And that's all based on the properties of tangent. Look at this. All real numbers except multiples of pi over 2. At pi over 2, it would be undefined because it puts 1 over 0. Okay, and now you might see a pattern here. You can go to 3 pi over 4. You can go to pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and then back at 2 pi. So these are the nicest values we could pick in order to graph tangent. Okay. But also, to make our work easier, since tangent only repeats itself every pi, that's what we're going to start with. We're going to start with negative pi and then go around the unit circle. So negative pi, which means I should get negative 3 pi over 4, negative pi over 2, negative pi over 4, and 0. And then start at pi over 4, pi over 2, 3 pi over 4, and pi. So these are the coordinates we'll pick for tangent, and once again, they are the easiest ones to graph it with. We don't have to do 2 pi, negative 2 pi to 2 pi because tangent repeats itself every pi. So we don't have to use those unless you really wanted to. Okay, so now when you plug in all these values to tangent, tangent at pi, negative pi is 0. Tangent at 3 pi over 4 is negative 1. But since it's an odd function, you'll have a negative weighting on the outside, so we'll just get 1. And then undefined at pi over 2, negative 1, 0, 1, undefined, and then negative 1 and 0. Okay. These are the parent function coordinates for tangent. These are the nicest ones to graph it with. Okay, so let's go ahead and plot it. All right. So negative pi, negative 3 pi over 4, negative pi over 2, negative pi over 4, 0, pi over 4, pi over 2, 3 pi over 4, and pi. Okay. And I'll put 1 here, and I'll put negative 1 there. Okay. All right. Now, let's go ahead and plot the vertical asymptotes first. So at the negative pi over 2 and pi over 2. Let's plot those. So you'll have a vertical asymptote there and a vertical asymptote there. Okay, those are plotted. And now we can go ahead and plot the rest of the points. So at negative pi, we are at 0. Negative 3 pi over 4, we are at 1. And then negative pi over 4, we're at negative 1, 0, 1. And then 3 pi over 4, negative 1, and 0. Okay, so I'm going to graph the middle piece so you get an idea of what tangent looks like. Okay, so you will follow, I should do a color, there you go. You'll follow this vertical asymptote down, and then you'll come, curve up. Oops. And follow the vertical asymptote upwards. That is the graph of tangent. Well, one piece of it. Should be a little bit curvier, but you know, my graphs. Okay, which means over here, same thing on the right side. Come from below and curve, 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 and follow up. And same thing here. Come from below, curve, 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 and follow up. This is the graph of tangent. There you go. And just like it says in the properties, your domain's all real numbers, except that integer multiples of pi over 2. Your range is all real numbers. These tails all go to positive and negative infinity. Tangent is an odd function, so it reflects across the origin. So this point here is pi over 4 and 1. And that point there is negative pi over 4, negative 1. And then it repeats itself every pi. So you see this exact same graph repeated almost every pi. Okay. And then the x-intercepts are multiples of pi. So you have an x-intercept here, x-intercept there, and an x-intercept there. And vertical asymptotes occur at integer multiples of pi over 2. So once again, at negative pi over 2 and pi over 2, you will have vertical asymptotes. Okay, so in my math lab, because I think it wants you to find the domain and range of these functions to state it. So even though it's stated above, I'll show you how to write it. So the domain, we're going to state it as, and I think it uses fancy set notation. So we're going to say for all x such that x cannot equal pi over 2k, where k is an integer. an odd integer at that. So k and the reason we state it's an odd integer is because, well, you're going to have vertical asymptotes at every odd multiple of pi over 2. And I don't think you have to state this. It might state it for you already, but this is the format it's going to want it in. So if you're wondering what k is, k represents any integer. If you're wondering what an integer is a whole number from negative infinity to positive infinity. Okay, so that's good for domain. And then for range, I wanted to fit them all in there. Maybe I can. Let's see. There we go. And range, I think it just says all real numbers, but you know that range is negative infinity to infinity. Or if it uses fancy set notation like domain, I don't know why it goes back and forth, just to make our life difficult. Fancy set notation would be for all x such that x belongs to the set of all real numbers. So it is good to know interval and these fancy set notations, just so you know how to read them. So with this, that lovely little vertical line means the words such that. So when we read set notation off, we say for all values of x, such that x belongs to, so that funny looking E means belongs to or is an element of the set of real numbers, that double type R. And that's how you read set notation. The one above, we would say for all x, such that x cannot equal pi over 2k, where k is an odd integer. Okay. So that's reading set notation. I don't think you could put, I think that's why it does set notation for domain, because you can't put the domain for tangent in interval notation, because you'd be writing a lot, because it breaks at every negative pi over 2. So you would have a lot of union intervals. So maybe that's why they use the set notation instead of interval, just for domain. Okay, let's move on. All right. Next, we get to the graph of cotangent, which happens to be the reciprocal function of tangent, which shares the exact same properties, well, almost the exact same properties of tangent. So the properties of cotangent is now that the domain is all real numbers except integer multiples of pi. The range is all real numbers, just like tangent. Cotangent is odd, just like tangent. Cotangent repeats itself every pi, just like tangent. And the x-intercepts are odd multiples of pi over 2. And the vertical asymptotes will occur at integer multiples of pi. So remember that domain and asymptotes work hand in hand. Vertical asymptotes. Okay, what numbers do we pick for cotangent? The same exact numbers we picked for tangent, only because they're reciprocals of each other. And this time, let me get it right, cotangent puts x over y. Yes, that is correct. Proud of myself. So you would use 0 because it puts 1 over 0, which is going to give us undefined. You would do pi over 4, because that would give us 1 again. You would do pi over 2, which gives us 0 this time. 3 pi over 4, and pi. These are all the numbers we're going to need. Negative and positive. Okay. So same exact numbers. So negative pi, negative 3 pi over 4, negative pi over 2, negative pi over 4, 0, pi over 4, pi over 2, 3 pi over 4, and pi. I wrote those much neater than the ones above. Okay, so looking at pi, cotangent at pi. Cotangent puts x over y, so you get negative 1 over 0, which right off the bat gives us undefined. Cotangent at 3 pi over 4, at negative 3 pi over 4. Since cotangent is odd, the cotangent of 3 pi over 4 is negative 1, but there's that negative weighting on the outside, so cotangent of 3 pi over 4 is 1. And then at pi over 2, you'll get 0, pi over 4, you'll get negative 1. And then at 0, guess what you get? Undefined, and then repeat. 1, 0, negative 1. Undefined. All right. Let's go ahead and graph. Write our intervals. Negative pi, negative 3 pi over 4, negative pi over 2, pi over 4 is 0. And once again, we go to 1 and negative 1. Now let's draw our vertical asymptotes. Happening at pi, happening at 0, and pi. So negative pi, 0, and pi. Okay, plot our points. Negative 3 pi over 4, we're at 1, 0, negative 1, 1, 0, negative 1. Now we graph the function and almost the same exact as tangent, just flipped around. We come down, curve, 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 follow that down. Same thing here. Come down, curve, 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 follow that down. And there is cotangent. And once again, you can see that it's odd. You got pi over 4 and 1. You got negative pi over 4, negative 1. They both reflect over the origin. On this one, you can actually see more clear than tangent, how it repeats itself every pi. You got the same exact graph here, the same exact one there. Okay, and you see your vertical asymptotes at integers of pi, and let's state our domain and range. Let's make it fit. So my domain would be for all x cannot equal pi k. And for this one, we can just state k is any integer, because it says it only happens at multiples of pi, integer multiples of pi. So k can now be anything at once. All right, range. Well, once again, you see your tails go to negative infinity up to infinity. So range is negative infinity to infinity, all real numbers, or the fancy set notation. Okay, perfect. That's cotangent. Yeehaw. Next is cosecant, which is the reciprocal of the sine function. The reciprocal of the sine function. Okay, so first off, read off the properties. The domain of cosecant is all real numbers except integer multiples of pi. The range for cosecant is greater than or equal to 1 and less than or equal to -1. What's that gonna look like? Cosecant is odd, which means it reflects across the origin. The cosecant function is periodic with a cycle, a period, a revolution of 2 pi, and there are no x-intercepts. We do not cross the x-axis. Now it's really intriguing, right? The vertical asymptotes occur at integer multiples of pi. Okay, well now, what do we pick for the cosecant function? Once again, that's why I posted the unit circle here. Okay, so let's start it off. Let's look at 0, at 0 radians, 0 degrees. Cosecant is the reciprocal of sine, which means we're only looking at the y values of every coordinate, and we want the reciprocal of them. Okay, so we start with 0, and if the coordinate of y is 0, what's the reciprocal of 0? The reciprocal of 0 is always undefined. So we can work with that. Undefined means we're going to get a vertical asymptote. Okay, let's move over to pi over 6. Look at the y coordinate there, 1/2. What is the reciprocal of 1/2? 2. We can use that. That's perfect. Then, pi over 4. Look at that y value, square root of 2 over 2. Do we want to graph the reciprocal of that one? Not at all. You're out. Look at pi over 3. Do you want to graph the reciprocal of square root of 3 over 2? No. You're out. Look at pi over 2. What is the reciprocal of 1? 1. That checks out. And then we go the other way. Look at 2 pi over 3. Look at the y value there. We don't want the reciprocal of that. 3 pi over 4. Do we want the reciprocal of square root of 2 over 2? Don't want that. Pi over 6. Do we want the reciprocal of 1/2? Yes, that's going to give us 2. So that's going to work out. And then we can end at pi because the reciprocal of 0 is once again undefined. And if you look at it, we have enough values to graph cosecant. You've got 1, 2, what do we got? 3, 4, 5. So we can, so for cosecant, we'll go from -pi to pi again. So that's all we're going to need using these values. So, but in between, we're going to pick pi over 6, pi over 2, 5 pi over 6, all that good stuff. Okay. So a little tricky for these functions. You got to know which ones are going to graph nicely. Sure, we can grab any number on the unit circle and graph it, but if we're graphing, we want nice numbers to plot. I don't want to plot the reciprocal of square root of 3 over 2. That's just me. If you like that stuff, go ahead. So here's what we're going to choose. -pi, -5 pi over 6, -pi over 2, -pi over 6, 0, and then repeat. Pi over 6, 5 pi over 6. Let's leave it as an ugly 5. Can't. Pi over 2. Oops. Nope. Messing all that up. Pi over 2, 5 pi over 6, and pi. Okay, So cosecant at pi is going to be undefined. Cosecant at negative 5 pi over 6 is going to be negative 2. And then cosecant at negative pi over 2 is going to be negative 1, and then negative 2, and then undefined. And then repeat the numbers, but now they're going to be positive. Cosecant at pi over 6, 2, 1, 2, undefined. Come on, laptop. Being real slow today. Okay, so plot the vertical asymptotes first. Oh, well, label your graph. See, keep getting ahead of myself. Negative pi, 5 over 6, pi over 2, pi over 6, 0, pi over 6, pi over 2, 5 pi over 6, and pi. And then we go up to 2 now. And down to 2. Okay. Plotting. Vertical asymptotes first. And then now plot our points, negative 5 pi over 6 and negative 2, negative 1 and negative 2. That one's way off. And then pi over 6 and 2, 1, 2. Okay, well, guess what type of graph we're going to have inside between our vertical asymptotes? You're going to have the graphs of parabolas. There you go. And that is the graph of cosecant. Okay, there is something really, really cool. Since cosecant is the reciprocal of the sine function, guess what fits nice and neat between the two parabolas? If you guess the sine function, you are correct. So you would have that would be the sine of x. It's pretty insane, right? So the reciprocal function gives you parabolas, but sine fits nice and neat in between those two parabolas. Something cool, and maybe something to think about. Maybe something to think about, or maybe it's just cool. All right. Okay, so there's cosecant. Let's get domain and range, as it's stated above. So domain for this domain would be for all x such that x cannot equal pi k, where k is any integer. And then range, it's already stated in the properties above. I think it wants it in the set notation. So range is going to say for all y's, y is less than or equal to -1. and y is greater than or equal to 1. As you can see from the graph, you go -1 and below, and you go 1 and above. If you were to put this into interval notation, you of course would have -infinity to -1 union 1 to infinity. That would be for the range. Okay. All right. I'm going to pause this for a second. My laptop is being really slow. So I'm going to disconnect and reconnect. One moment. Okay. Well, hopefully it works. So that was the graph of cosecant. Now we get to our final page, which is the graph of secant. Secant is the reciprocal function to cosine. So once again, we have to be careful about what numbers we're going to pick up the unit circle. Okay, properties of secant. The domain is all real numbers except odd multiples of pi over 2. The range is just like cosecant. It goes from -infinity to -1, 1 to infinity. Secant is an even function, meaning it reflects across the y-axis. Secant is like cosecant, and like cosine and sine, they all repeat themselves every 2 pi. There are no x-intercepts, and your vertical asymptotes go along with your domain, and they will occur at odd multiples of pi over 2. Okay, so looking at our unit circle, what value should we pick for the secant function? And we can start at 0. Secant only looks at the x values. So what is the reciprocal of 1? That's 1. That checks out. Then we look at pi over 6. Look at the x value only. Do you want to grab the reciprocal of square root of 3 over 2? No. Look at pi over 4. Do you want to grab the reciprocal of square root of 2 over 2? No. Look at pi over 3. Do you want to grab the reciprocal of 1/2? Yes. That gives us 2. Look at pi over 2. If we graph the reciprocal of 0, that will give us undefined. So you're seeing that this is very similar to cosecant, but only with different radian values. And then we make a way around at 2 pi over 3, the reciprocal of -1/2, -2. That checks out, gone, gone, and we stop at pi, and the reciprocal of -1 gives us -1. So what we're going to choose for secant is going to go from pi to -pi over 3 to -2 pi over 3, pi over 2, and pi. So those are the values we're going to choose. I know I said it out of order, but I'll write it in order on the table. Okay. Right there. Okay, so once again, start at -pi. Then we'll go -2 pi over 3, -pi over 2, -pi over 3, 0, and then everything is just positive. Okay, so secant at -pi, secant is even, so no matter what, it's going to be -1. So -1, and then we'll get -2, and then we're going to get undefined, and then you are going to get 2, 1, 2, undefined, -2, -1. Okay. And these are the parent coordinates for secant. Let's graph. Okay, got it labeled, and then vertical asymptotes first. And negative pi and negative 1. Negative 2. And then, where do we have? 2, 1, 2. And then negative 2, negative 1. Okay, so we have our points plotted, and just like cosecant, secant is also going to have parabolas inside its asymptotes. So the first one, and then I'll do the one on the right. And then the one on the left. Good. And there we go. That is the graph of secant. No x-intercepts, it's even. It reflects across the y-axis. Those 2 points are the same, or even, not the same, but just reflected across. Or this point and that point reflect all across the y-axis. Okay, so we're even. We repeat ourselves every 2 pi, and then we just want to label domain and range. Okay. So we see we have vertical asymptotes at every odd multiple of pi over 2. So to state that, we'll say domain for all x such that x cannot equal pi over 2k, where k is an odd integer. And then range is just like cosecant. I'll write that in here. Range is for all y such that y is less than or equal to negative 1, y is greater than or equal to 1, or interval notation, negative infinity to negative 1. Union 1 to infinity. And there it is. Those are the graphs of the remaining 4 trig functions. Just know the parent function's coordinates, know which ones to pick from the unit circle. And I didn't do any transformations on here, but in case you get transformations, I assume you know how to handle those. I guess one thing I should voice out is that if you are not using transformations, if you're using key points, then for, what is it? For tangent and cotangent on key points, for key points, your subintervals are going to be a little different. Your main interval will be from 0 to, what is it? Pi over b. Or no, pi over omega. Normally it's 2 pi over omega, but since it's tangent and cotangent, they don't repeat themselves every 2 pi. They repeat themselves every pi. So you would just have to change these up. Okay, so that was just my little word of caution if you're using key points. Transformations, easy all day. You have the parent function coordinates here. Remember them, transform them, and done. But other than that, we are done with those last 4 trig graphs. The next section is more graphing. It'll involve something called phase shifts, which are just horizontal transformations to the left or to the right. We put a fancy name of phase shifts on it because we're fancy. All right, till the next one. See you there.